This is problem 13.188. It's on page 909. When the rope is at an angle of alpha equals 30 degrees, the 1 pound sphere A has a speed of v naught equals 4 feet per second. As I read this, let me make a sketch and write down all this information. So the angle alpha is 30 degrees. This is 1 pound, let's just say 1 lb sphere. And it has a velocity v naught of 4 feet per second. Now it's going to swing down and hit, so actually let me move this over. It's going to swing down in such a way that right when the string or rope or whatever is vertical, it'll hit a cart that has an angled face. I may make some mistakes along the way as I work this one because I haven't written this one out yet. Basically, the cart cannot move except for horizontally, despite my poor wheels. And there's a spring at the back connected to the rear of the cart that supports the cart. Okay, so the cart's going to move. The question is how much, I guess. Anyway, coefficient of restitution between A, that ball, and the 2 pound wedge, so this must be a 2 pound wedge. We call this B apparently in that A. The coefficient of restitution E is equal to 0.7. And the length of the rope is length of the rope is 2.6 feet. The spring constant has a value of 2 pounds per inch. And the angle theta, which is right in here, is 20 degrees. Determine the velocity of A and B immediately after impact, maximum deflection spring. Assume A does not strike B again before this point. So we'd like to know delta x of the spring, let's call it, and velocities after impact. So delta x is how much? And VB prime, VA prime, so to speak. Okay. Any questions about this problem? I have a question. How the heck are we going to solve it? Well, just like anything, how do you get an elephant one bite at a time, right? Take a big problem, break it down into smaller pieces. The first thing let's do is figure out how fast the ball's moving once it hits. How could we do that? What tool in our toolbox makes the most sense? F equals MA? That's the one we don't want to reach for, right? That's the knuckle buster wrench. You want to avoid that one if you can. What else could we use?
Use energy balance.
Energy is the easiest way to go most times because you don't have to worry about direction. So basically what's going to happen is the weight's going to fall. How high will it fall? I don't know. We call it delta Y. And so we could say that the initial kinetic energy plus the work of all the forces from state 1 to state 2 equals the kinetic energy in state 2. Of what? Well, of ball A. So 1/2 MA V naught squared, and then minus W delta Y, where this must be the weight of A, because I'm only talking about A right now, equals 1/2 the mass of A times the velocity of A squared. And I'll use this for, being in this position when the problem really starts, right? So the ball would have a velocity in this direction. It has to be, right? Because that's perpendicular. It has to be perpendicular to the string of VA when it strikes the surface of the wedge. Okay, let's see if we can put a number to this. The weight of A is nothing more than MAG, so we can cancel the mass of A out of the whole thing and save ourselves a little bit of time. We'll have to figure out delta Y, probably do that from geometry. Let's see. It's going to be a little bit of a pain, but it won't be too bad. So let's see, let's draw a triangle over here to indicate the ball's movement. Something like that. And since we have a 2.6 foot side here, an angle of 30 degrees, then we can figure out the length from here to here, right? We can figure out this base length. Is that the sine side or the cosine side? That's the sine side, isn't it? So this side would be 2.6 foot cosine 30 degrees. So what do we get for that? 2.6 cosine 30 is how much?
1.3?
1.3. I can never remember for some reason the cosine of 30 is a half, but there it is. I get confused between sine and cosine of 30, which one's a half. Okay. And I'm sorry, I said, you told me it's sine and I used cosine. Sorry, my fault.
It is 1.3.
1.3. Thank you. So you did the right thing and I wrote the wrong thing. You guys are correct on me. Good job. Thank you. So I guess it's, see why I can't remember whether sine or cosine of 30 degrees is a half? Because I make mistakes. All right, so 1.3 feet. And that's not really the side that's interesting, though, I don't think. I think I should have I should have gone with the other side, right? Because I know that the length from here to here is 2.6 feet. If I just had this, I could take it from 2.6 and be done. So let's not waste any more time. Let's get this side length. That would be 2.6 feet times cosine of 30 degrees. And if I were a liar, I'd tell you I'd planned it and I actually was thinking of that side, but I wasn't. I was just making mistakes. So I think cosine of 30 is like 0.866 something. I don't remember what it is. So what's 2.6 times cosine of 30? Because we do need that one also.
2.251?
2.251, and it's rounded off, of course, because cosine of 30 is not rational. Okay? So 2.251. So that means that the height, or the amount of drop that the ball experiences, delta y, would be this distance, and that distance is 2.6 feet minus 2.251 feet. Right?
0.348.
0.348, thank you. Bless you. Is it really? Is delta y really 0.348 feet? Do I need to plug in 0.348 feet here?
It should be negative.
It should be negative, that's right,
Because you're
because we're taking positive y upward for this part of the problem, because that's opposite to the direction of gravity, right? So it's actually a negative 0.348 foot drop. Okay. All right. What I really want to know is the velocity at the end, so let's solve for that. That'd be v naught squared plus, what are we in? We're in English, 32.2 feet per second squared times 0.348 feet. Notice what I did there, I just canceled the negative sign. And I need to remember I'm multiplying through by 2. There we go. I wanted to multiply through by 2 to get rid of those halves. And so all I really need to do is plug in V naught, which is 4 feet per second, and square it, and then take the square root of the whole thing, and I'll have VA, won't I? So this is root 16 plus, I can't do that in my head, I can do this much, 64.4, how's that? And 0.348. Units are all the same, we'll come out in feet per second. It's really consistent. Punch it into your calculator for me, please, and let me know how this comes out. Looks to me like 34.8 or 34.8%, if you will, of 64. Roughly 33%, 21-ish. 21 and 16, or 37, which is close to 36, so I'm guessing it's about 6 something.
6.20.
6.20?
I can type it.
Wait. Okay. Oh, you're right. My brain's stupid.
Sorry. Did I get that 6.20, is that right? So that's the velocity. Here's what I want you to notice. We don't really care about any of this anymore. That was a side quest. That's all that. Our side quest still a thing, I have no idea. I like watching Viva La Dirt League. If you've never seen it, they make fun of video games and some of the crazy stuff in video games. It's pretty funny, especially if you played any video games. So now we're at this point, and we have a new problem basically, and that is that the velocity of the ball is 6.2 feet per second when it strikes the wedge. Okay. Now let's set that up differently. Let's get rid of some of this, because we're pretty much done with the energy analysis part. We have a new problem to work on. This is the next step in the process. Let's draw this again. Let me draw ball A. Let me draw the wedge. And notice that the line of impact normal to the surface of the wedge is at 20 degrees. Right? So despite my drawing, this line is at 20 degrees with respect to the horizontal. Forget about the y that we had before. Okay? I don't care about that coordinate system. I want a new coordinate system, something that makes my life easier. It's kind of like putting a tool back in the toolbox and reaching for another one. Okay? I'd like a coordinate system that looks something like that, because I think that'll make my life easier. I can analyze it now. Okay? Now, what direction do you think should have no change in momentum for A? Why? You would think that. Notice there's, let me push back on that just a little bit. Notice that there is tension in the rope while the impact occurs. There's also weight acting downward. There's weight acting downward on the wedge, so weight of A, weight of B. There's also somewhere in here a normal force acting up on B. Because if we apply a force this way, and yet the thing can only move horizontally, then there must be enough reaction to cancel out the downward component. So now, what do you think about what forces act on the ball during impact? Does the weight act during impact? Not really. Why? Because we're making the assumption that the impulse from the impact force is going to be much larger, because that force is going to be much larger. We're making the assumption that this impact will happen over a very short period of time. It will be a very large force, and so we can neglect the weight. So what are we going to do with the tension and the strength? Neglect it too, right? Now notice that in general, if they had put the surface like this, we might not be able to neglect the tension in the string, because the string would be stretched a little bit, right, or pulled, and we assume that it's perfectly extensible, it's perfectly solid, in the sense that it will not stretch at all. In the real world, of course, every rope is very elastic, right? Even wire rope is fairly elastic. So basically, we're going to neglect these two. We're also going to neglect the weight of B, because it will be small. Can we neglect this normal force on B? We can't, because this normal force has to be large enough to cancel whatever, let's go back to a regular vertical coordinate system, whatever component of the force that acts this way, we need to cancel the downward part of it, right? Because it's not like B starts moving down for a second. No, it has to move only horizontally. So this is going to be a significant force. But the weight of B, the weight of A, and the tension in the string, because of the orientation of the surface, will all be negligible. Okay? So I pushed back a little bit and made you wonder, well, wait a second. Does the y component of the ball's velocity change? The answer is no. Because notice the force is only in this direction, the y direction is normal to it. So if we could get the y component of velocity before impact, we know something about the y component of velocity of A after impact. So let's do that. Now this is not an extreme angle, so getting the y component of velocity should be pretty easy, because notice the ball's just moving kind of like that, right? So there's a 20-degree angle in here. So the velocity of A written as a vector, just like the last problem, will be the initial velocity, VA, the magnitude of the velocity, I should say, times the cosine of 20 degrees in the I direction plus the sine of 20 degrees in the j direction. Right? So let's make these numbers. VA is 6.2 feet per second. So what's 6.2 times cosine 20? What's 6.2 times sine of 20? Let's just make numbers out of all this. The last problem was almost all symbols. This one, let's make them practically all numbers.
6.2 times cosine of 20 is 5.83.
Could you give me one more decimal, please? If you don't have it, it's okay.
5.826.
2.6, thank you. Somebody else for the sine component?
2.1205.
Let me make it 1. I'm just going to go to 3 decimal places. J, and that is feet per second. Like I said, it's this component that doesn't change. So VAY prime is 2.121 feet per second, isn't it? Now that's not all of the velocity of A after impact, that's just the Y component. Now we have to consider what happens to the X component. Okay. If I were to write the momentum of these two bodies along this x-axis, could I say that momentum is conserved for the two bodies? No. There's an external force acting that will prevent the momentum from being conserved. But could I include it in my equation? Sure. So let's do that. So the mass of A times the velocity of A in the x direction, which we know what that is, 5.826, plus the mass of B times the velocity of B in the x direction, which we know is 0, because B is not moving before impact, plus the integral of the normal force at B, but we don't want all of this force, we just want the x component, right? So let me say NBX, realizing that that component is going to end up being negative, okay? That acts over time equals the mass of A times the velocity of A in the x direction prime, plus the mass of B times the velocity of B in the x direction prime. Will B have a component of velocity in the x direction? Yes. Will it have a component of velocity in the y direction? Yes. And those two are related to each other also, aren't they? Now this is an x direction momentum balance, and it includes this term. Now this term, NBX, we know is just going to be negative NB times, well, let's see, NB is like this. The triangle I want to build is, let's see, I want an XY triangle, so there's the X side. No, that's not the way I want to do it. Let me try again. There we go. Let me make it bigger. There we go. NB. There's the Y side, there's the X side. There we go. So you see that NB has a negative X component. The 20-degree angle, let's see. I know we've got a 20-degree angle there. So the other 20-degree angle is here. Mutually perpendicular lines. So, if that's the case, then this side would just be negative NB times sine of 20 degrees. And this side is just NB cosine 20 degrees. So far so good? Yes.
Do we need to factor in any force from the spring in the x direction?
That's a good question. Let me answer that in just a second.
Okay.
Let me keep myself straight here.
Okay.
I only wanted the x component, so I better not forget to put in sine of 20 degrees. Okay? Is the spring compressed initially? No. During the impact, is the thing going to move much? No. The spring force is even more negligible, I would say, than the weight.
Gotcha.
So for the same reason, though, that I said the other forces, the weight force and the tension of the string are zero, I would say even more so the force in the spring is zero, because it's a small force for that short period of impact time. Okay, so I don't want to forget that the other side is NB cosine 20, but I think I can remember that. I just don't need a negative sign on it. What about the y direction? Could I say anything about the y direction? Sure. Would I have to apply the y direction equation to the ball only? No, I could apply it to the wedge. If I apply it to the wedge only, then I think what will happen is I'll have an internal force between the two that I don't really want to deal with. I'd rather not deal with it. I could do it, but then I'd have to sum momentum in the y direction on the ball, and that wouldn't be very useful to me. Putting them together, I think I'd get the same thing. As if I just write mass of A, velocity of A in the y direction, that's before impact, plus the mass of B, velocity of B in the y direction, which it wasn't moving before, plus only external. Why? Because all of the forces that happen in impact are internal. I'm dealing with the momentum of both the bodies, right? And that force is internal. This one is external. So for the same reason that I needed this term in the x direction, I'll need a y term in the y direction. So remember, that was just NB cosine of 20 degrees dt equals, and on the other side I'll have mass of A, velocity of A in the y direction prime, plus mass of B, velocity of B in the y direction prime. Right? It's really just a momentum equation in the y direction, just like the x direction. However, you might look at this and say, oh my goodness, these are a lot of terms. It's not as many as you might think. We actually know all of this. That's easy. We don't know NB. We don't know how much time. Of course, what we're going to do is we're going to take NB out as if it's constant, right? So we're going to take it out and just have NB delta T, essentially. We do know something about the velocity of A in the y direction after impact. Remember, we already determined that. The velocity of A in the x direction after impact, not sure. How about these terms, velocity of B in the x direction and the y direction after impact? We know something about that. What do we know? Well, we know that VBX prime, how do I want to say this? These two have to add up. Let's do it this way. If this is the velocity of B in the x direction after impact, we have to have enough velocity in the y direction after impact so the net velocity, VB after impact, is horizontal. Because that's the only way it can move. Basically what this does is this puts a constraint on these two, which controls how much normal force we must end up with. Okay? Now, I'm looking at this and I'm a little concerned because it looks like we've got really 1, 2, 3, 4, 5 equations. NB I don't want to count it twice, of course. But I'm only, or 5 unknowns and only 2 equations. Well, let's see what we can do with that. However, I've got another restriction here. So that's at least 4 or 3 equations. What else, what other equation might I write?
The coefficient of restitution.
Coefficient of restitution equation, E, okay? Now, it may be that I can solve some of these and I don't need to solve for everything. All I really want are the velocities after impact. So let's see what happens. All right, so let's put this into an equation form. Let's see. Really, isn't this a right triangle? And isn't this angle 20 degrees? So can't we say that, let's see, VBY, in fact, let me put this somewhere where I can hold on to it. VBY prime, this component, over VBX prime is equal to tangent of 20 degrees, right? Because look, it's just a right triangle. There's the y side, there's the x side. If we really wanted to, another way to say this would be that, we could write it, so let me make this a big or. VBY prime equals VB prime. Let's see, in the y direction, times sine of 20 degrees, and VBX prime equals VB prime cosine 20 degrees. I don't know which one will be more useful between these. Probably this, so I can just plug in directly for VBX and VBY after impact. That way I'll turn these two into one unknown. In fact, I think I'll do that. I don't think I'll go with this one. So let's just make that substitution right here. VBX prime, we will write as VB prime cosine 20 degrees. And VBY prime, we'll just write as VB prime sine of 20 degrees. So far, so good? So now we have VB prime as an unknown, VAX prime as an unknown, time and NB. So we got 4 unknowns now. 2 equations, 4 unknowns. Because what I've done is I've used up one of my relationships, right? I've developed it and then baked it into the equation. Now, let's see, what else? Let's see, oh, the coefficient of restitution, we're going to use that next, so let's write that one down. The coefficient of restitution, E, will only relate what's going on in this horizontal direction, right? So, let's write it that way. We want the velocity after impact, or the relative velocity after impact, in the x direction, divided by the relative velocity before impact, but opposite order, right? So we have a positive thing here. So that our coefficient of restitution is positive. Now, before impact, B was not moving, therefore its velocity in the x direction is 0 before impact. And what this does for us is relates the horizontal component to the horizontal component of A after impact and the horizontal component of A before impact. So let's see, VAX, this is known, and now we have another equation with 2 unknowns. Now, really, you know what we could do? We could make this back to VBX prime, and we could write VBY prime in terms of VBX prime. I think, so I'm actually going back and using the equation I had, VBX prime under VBY prime equals tan of 20 degrees. So let me make the substitution that VBY prime equals VBX prime tan of 20 degrees. And so basically I'm going to put that here. So I needed VBY prime, I will write VBX prime tan of 20 degrees. It's still just one unknown, but I think that might make it a little bit easier. Okay? So that way it appears directly in this equation. Otherwise I'd have to substitute VB times cosine of 20 degrees or something. Okay? All right. Okay. Now, I don't really want the time. Let me erase the figure because I think we've finished with it. Let me rewrite the x and the y equations. MAVAX, not worried about that. I've got all those, that's just a number. I'm going to stop writing these because they're 0. Minus NB sine 20 degrees times whatever time occurs of impact. That's just this integral. Equals mass of A, velocity of A in the x direction prime, plus mass of B, velocity B, the x direction prime. When we keep track of my unknowns, T, NB, VAX, and VBX. In the y direction, MAVAY plus NB cosine 20 degrees times time equals MAVAY prime, which remember we know that, that's right over here, plus MB VBX prime tangent 20 degrees. Did I introduce any new unknowns? VBX prime, T, and B? No. So I've got one equation and three unknowns here. Is there something else I'm missing? I feel like I'm missing another relationship. Notice it has nothing to do with the spring, right? We're not to that point. We need to figure out the velocity of B before we can figure out how far the spring is compressed. No, I think we've got everything. All right. Well, I could rearrange this and get rid of VBX in favor of VAX prime, but that would still leave time in NB. Notice though, they didn't ask for the normal force. They didn't ask for the time. Well, couldn't I just combine those two as a single unknown? I can't solve for either one, but I could solve for that as a single unknown and eliminate it between the two equations. I like that. Let's try that. In fact, let's see, if I multiply this whole thing through by cosine of 20, and I multiply this whole thing through by sine of 20, I'll get rid of those in one fell swoop. Let's try that. That seems like a good idea. So basically, I'm going to multiply the x direction equation by cosine of 20 degrees, whole thing, left and right. And I'm going to multiply all of the y component equation by sine of 20 degrees. Do you see what happens? Sine of 20, cosine 20, NBT, positive. Cosine 20, sine 20, NBT, negative. You see that? So then when I add them together, those terms will just go away. So let's see, let's add them together. Cosine 20 MAVAX plus sine 20, not sine squared, sine of 20 degrees, MAVAY, that's these two, plus nothing, because those two just go away, equals, don't forget we're multiplying cosine through everything, so cosine times that, cosine 20 degrees, VAX prime plus cosine 20 degrees, MB, let me not forget my mass of A here. Cosine 20 degrees, mass of A, cosine 20 mass of B, VBX prime. And for the Y, no, we're adding, so we've got to add to that sine of 20 times this. So sine of 20 degrees, MAVAY prime, plus sine of 20 degrees, VBX prime, tangent 20 degrees. Looks like a mess, but I think we're closer. We got rid of two unknowns in one fell swoop there. And like I said, we can use this equation to get rid of, say, VBX. So we'd have EVAX, just multiplying through, plus VAX prime equals VBX prime. We could substitute that in for VBX prime, and then I think we'll be able to solve it because the only unknown will be VAX prime, won't it? Now that's a little bit of a pain, but we can do it. Let me show you how. Let's continue just a little bit, a little more math, a little more algebra, and we'll be done. Okay, so cosine 20 degrees, mass of A, VAX, plus sine of 20 degrees, MAVAY equals cosine 20 degrees, MAVAX prime. Let's see, plus cosine 20 degrees, MB, and we'll need VBX prime, but that is just EVAX plus VAX prime. That finishes that one. Plus, and let me move over here, plus sine 20 degrees MAVAY prime, plus sine 20 degrees MBVBX, well, I didn't want VBX. I wanted EVAX plus VAX prime, tangent of 20 degrees. Now, if I didn't miss anything during copying, I think this is what we have and what we need. So VAX prime is the only unknown, right? But of course, it's a little bit of a mess. If I were to solve for this algebraically, I would probably make a mistake. So I'm probably going to just throw this into Excel and goal seek it and be done. Yeah. The other way to approach this would just be to put in numbers for all of this. I'm just getting tired of writing symbols. Most of these things are just numbers. We know VAX, VAY before the impact. We know the mass of the various things. We might be able to simplify by plugging in masses. I mean, for example, the mass of A is just 1. So if we get rid of the mass of A everywhere it appears, because it's just going to be multiplied by 1. And B is just a mass of 2 pounds, isn't it? That looks a little simpler. I was thinking about dividing by cosine of 20 degrees everywhere, because if I do that, then this will become tangent of 20 degrees. Let's try that. So if I divide through by cosine of 20 degrees, this term right here would just lose its cosine of 20 degrees. But this term divided by cosine of 20 would become tangent of 20 degrees. If I divide this by cosine of 20, it would just go away. Divide this by cosine of 20, it just goes away. Divide this by cosine of 20, it becomes tan of 20 degrees. Divide this by cosine of 20, it also becomes tangent of 20 degrees. And notice I got tangent of 20 degrees twice, so that would be tangent squared of 20 degrees. Maybe I will go ahead and solve it, because it looks like it's becoming a little more friendly. We can refer back to the figure in the book. So let me get rid of the figure, because after we figure out how fast V is moving after impact, we'll be able to figure out the spring compression. So let's see, what do we got? VAX plus VAY tan 20 degrees equals, well, let me just pull this VAX to the other side, so minus VAX prime. And let's see, do we know VAX prime? No, we don't. I can't move that to the other side. That's the unknown. Okay. But I can move, well, that might be too confusing. Let me just copy it, because it's getting kind of confusing. VAX prime plus 2 times E. We don't need this anymore either. I hope I didn't make a mistake along the way, otherwise it's going to be really confusing to find. VAX plus VAX prime plus tan of 20 degrees VAY prime plus tan squared of 20 degrees times 2 times E VAX plus VAX prime. Okay. If I miss a term anywhere, please tell me. Just boring algebra at this point. So the only unknown is VAX prime, correct? Yeah, because we know VAY prime. So let's move everything to this other side. VAX plus VAY tan 20 degrees. We'll take this term to the other side, so minus 2EVAX. Check them off as we go. There we go. I'm going to leave this one on the right-hand side. Take this, so minus tan 20 degrees VAY prime. That's that term. And then minus tan 20 degrees squared 2EVAX, this term. Tan 20 degrees 2E, yeah, VAX. equals what's left, VAX prime plus 2 more VAX primes. That's that term and that term. And finally, plus 10, 20 degrees, plus 10 squared of 20 degrees, times 2 times E, no, not E. E won't appear on that, but the 2 will, VAX prime. There we go. Make it X. This right-hand side is just VAX prime times what? Well, 1 plus 2 is 3. And then plus 2 times tangent squared of 20 degrees. So all we have to do is divide this whole side by 3 plus 2 tan squared of 20 degrees. And we'll have it. All right. Seems like more of a problem than a solution, doesn't it? Any questions so far? Anything you think I've missed? All right, so VAX. That was the velocity of A in the X direction before impact. There it is. 5.826 plus VAY, 2.121, tan 20 degrees, minus 2 times, the coefficient of restitution was 0.7 if I remember right. VAX, 5.826 minus tan of 20 degrees. VAY prime is 2.121. Notice it's the same before as it is afterwards. Minus tan squared, 20 degrees. Well, let's put the numbers first. 2 times 0.7 tan squared, 20 degrees. Let's see, times VAX. VAX is, there it is, 5.826, all divided by 3 plus 2 times tan squared of 20 degrees. So what you do to figure this out is take the tangent of 20 degrees and then square it. If you wonder what tan squared means. Let's see, if we were to divide through by tan squared, would that help us or hurt us? Yeah, it wouldn't matter. However you want to do it. I think I'd take the tangent of 20 degrees, put that in memory, and then use it in this equation. Is there anything that simplifies? Oh, hey, here's something that simplifies. Why didn't I notice this? 2.121 tan 20, positive and negative. I should have noticed that. Well, it'd be hard to notice because one's a VAY prime and one's a VAY, but since they're the same before and after, then that goes away. That's kind of nice. Other than that, we could have factored out a VAX from the rest of it. That would have been all right, but oh well. What do you get for this?
I got negative 1.045.
Of course, the units would be feet per second, right? Now, there's a decent chance that I've made a mistake along the way somewhere.
There's a decent chance I typed something in wrong.
You or me, and we're not that far off, but
No, we're not. Hang on, I'm gonna get the single thought way too.
You know, I may be sorry I erased all that stuff. We need the velocity after impact. We've got the velocity of A before and after, except in the X direction. And I think I've erased my coefficient of restitution equation, but that's okay. Because I know that this came from the coefficient of restitution equation, so I'll be able to pick it back out here in a second.
I agree with that answer.
You agree with this one?
Yes.
Let's get a third, if you don't mind.
I didn't calculate, but I agree with it too. if you don't mind.
You're tired of the problem, so who cares, let's just move on. I think tangent of 20 degrees y over x is gonna be pretty small. So tangent squared is gonna be small.
Alright, I did it in a simplified way, got the same.
Same answer, okay, all right. So we'll call that the right answer for the time being, that's fine. So that gives us the velocity of A after impact. So we could write, let's see, let's just get rid of this because we don't
And
want
then,
it. So this is the velocity of A before impact. The velocity of A after impact would be negative 1.045 I, right there, plus 2.121 J feet per second. Now let's check something. This should be the velocity after impact. Before impact, the ball was just swinging down, right? So it was just moving this way. If the ball has a negative y component, I think we've got a problem, right? Because the rope would have pulled against that and prevented it. But if you notice, while we have a negative horizontal component, we have a positive y component, so everything's okay. So neglecting the tension of the rope is okay. Or basically, neglecting the tension in the rope is baked into this, and I think that our answer is reasonable. Okay. And then, if we want to calculate the velocity of B, notice that, remember that this was just the velocity of B in the x direction after impact. Remember that? And it was also then equal to the velocity of B times the cosine of 20 degrees because of the way that I set up the coordinate system. So let's figure out the magnitude of the velocity of B in the x direction after impact. That's 0.7 times VAX. This is the velocity in the x direction before impact, 5.826, plus the velocity of A in the x direction after impact. Well, that is a negative 1.045, and I'm sorry if I'm off the camera. I'm trying to say what I'm writing. I've erased my stop, so I don't know where I'm at. But remember that these preserve their sign, right? There's a directionality associated with these. So what is the velocity be in the x direction after impact? And understanding that it has to have enough y velocity that it's actually just moving horizontally, not in the x direction. Because remember, right now we're talking about a rotated coordinate system that's rotated at 20 degrees, right? So what's this number? 5.826 minus 1.045. You know what? I think I can do that. 0.7 times 4.8. Well, no, it's going to be 7 because I got to borrow. This might not be as easy as I'd hoped.
Should be 3.34 though.
What's that?
Should
Oh,
be-
you got the whole thing?
Yeah, it should be 3.35.
3.5. Okay.
Does E get multiplied by both terms? Or multiplied to?
Yeah, you got to add these two together first and then multiply by 0.7.
Okay, because that's not how it's written in the thing we took it from.
Oh, you're right. I made a mistake, didn't I? You're right. I should not have that. Let's try again. Yeah, my fault. Yeah, so it's plus a negative value. I got carried away with my parentheses. Thank you. So now what do we get?
Should be 3.03.
Okay. That's feet per second. And so now we can calculate the velocity of B after the impact. It would just be the velocity be in the x direction after impact divided by the cosine of 20 degrees. So take the number you've got there, divide it by the cosine of 20, and what do we have?
3.23.
3.23 feet per second. Now we need to be a little bit careful. Can't just stick an I on this. Why? Remember that this I and J refer to this direction, right? This coordinate system. And what I said before is not quite right. This is not actually in the vertical direction. This is in the slightly rotated vertical direction. So I probably should transform that back into a regular XY coordinate system. And then I could make more sense of this. So there's our velocity, but that's horizontal. That's a horizontal velocity, because it's the block, the wedge, is constrained to only move horizontally. Okay? So how could we transform this into an upright coordinate system? Or, yeah, because that's the one we're interested in after impact. That way we can double check and make sure that J is in fact a positive thing. Well, if you think about it, this rotated coordinate system has a positive y component and a negative x component, doesn't it? So actually, it's even better. Right? It's probably even more vertical. So let's figure out, let's go ahead and rotate it back and see what we get. If we take, probably a quick way to do this, and I don't know what it is. Let me just draw another coordinate system. We'll use a red color for this. And let's just have the red XY and the black XY. How's that? Then all we have to do is take the y component and the x component of the velocity, I'm just going to put it down here, and project them onto the xy axes. So let's see. If I want to write VA prime now, kind of hurts your heart to erase all that work, doesn't it? Doesn't mine.
It hurt more to write it.
Hurt more to write it? Well, we're going to get a contribution from both the y and the x directions in the y direction. In the new x direction, we're going to get a contribution from y and not so much, or we're going to have something taken away from the x. So, let me try another marker because I'm afraid this one's going to not work very well. So, here is the y component. So I'll just take 1.21, no, 1.121. And I'm taking this, I want to figure out how much that contributes to x. So if my 20-degree angle is here, then I need basically a cosine side. Let's see, that's not the way I want to look at it. I want to look at it this way. Yeah, so that's the sine side. So I need sine of 20 degrees. This is all in the x direction. So I'm just put parentheses around it. And I'll subtract from that. So minus 1.045 cosine 20 degrees. And that will all be in the I direction. And then if I want to figure out J, then I'll have, let's see, the vertical, which is, I'm sorry, I'm messing up like crazy here, guys. That's 2.121. I'll have 2.121 again. So I'll make sure I get this right. Cosine of 20 degrees plus 1.045, because that's the magnitude of this length. And it'll end up being the opposite trigonometric function, so sine of 20 degrees in the j direction. Okay. So go ahead and calculate that for me if you would, please. 2.121 sine 20 minus 1.045 cosine 20. Let's have this half of the class work on that. The other half of the class, why don't you work on the second term, the j term. You can't read it in my writing, just let me know.
So that is on the I term, it is a 1.045.
Cosine 20 degrees.
Okay, I didn't know if that was, yeah. Okay.
Yep.
What do you guys
Is
We got-
negative .257.
Negative 2.57?
Yes. 0.257.
0.257, I was gonna say, there's no way. I, okay, how about the J term? Hope it comes out positive.
J is 2.35. Oh, 4.
Should just said there. Back up that.
J will.
Anyone agree with that or disagree? It works? Okay. All right, good. So that means that A, when it bounces off, it comes back a little bit and is moving upward. So the tension of the rope's gonna go to 0. It's gonna go up for a little while. And we know the velocity of B. Really, the only thing we care about, we don't really care about any of this. They just asked for the velocity, so there it is. In a regular XY coordinate system, like that. The only other thing we really care about is that number right there. Because this is the velocity of the wedge after the impact. So the question is, finally, the last part, how far is the spring compressed? Now, my question to you is, what tool should we use at this point? Which one do we pull out of our toolbox? We want to know how far the spring is compressed. Your brain's about fried, isn't it?
I want to say energy balance.
Energy, absolutely, energy. T1 plus U1 to 2 equals T2. What am I saying here? Now I'm talking about block B, or the wedge, as they call it, right? And what happens is the block moves until it doesn't move anymore. In other words, until it runs out of kinetic energy. But it starts with kinetic energy 1/2 2 pounds mass times its velocity squared, 3.23 feet per second squared. That's how much kinetic energy it starts with, right? And then what happens? Well, then there's the spring that does work on the block, right? Or on the wedge. And we just need to go get the spring work equation, deal with that. Anybody have the page number? I don't remember where it's at.
Page 803, I think.
803 sounds about right. Yeah, there we go. So I think I'll use equation 13.6, which says take 1/2 K delta x1 minus delta x2. So 1/2 K delta x1 squared minus delta x2 squared. Remember, I prefer delta terminology to indicate the compression spring. Not that it matters much in this case, because the spring starts off in state 1 completely uncompressed, so that's 0. And so this will be the compression of the spring, which is what I want to know from this whole problem. Anyway, this will equal 0. So, at this point, it's not all that difficult. We can say do I want to move that? Yeah, let's just do this. We'll cancel a half. So we'll say 2 pounds mass times 3.23 feet per second squared equals K delta x2 squared, right? Because that's all that's left. All I've done is take this to the other side, so that's where the negative sign got off to. So if I just divide this by K and take the square root, I'll have how much the spring is compressed, which is the question. So the spring constant K they gave us, how much was it? Does anybody have it?
2 pounds.
2 pounds per inch? Thanks. 2 pounds force per inch. But wait a second. We've got a couple of conversion factors here to deal with, don't we? I don't like these pounds mass and pounds force. I need to convert. I can't convert pounds mass to pounds force, but I can convert pounds force to pounds mass feet per second squared. So I will want something that has pounds mass over something that has pounds force, and the pounds mass better have feet per second squared in it as well. Let's give ourselves a little more space. Well, what number do I need and where do I put it?
Be 2.2.
32.2, does it go with this or this?
Top.
The top. That's right.
2.2 pounds mass per second squared.
That's right. So now, pounds, Siobhan, pounds, what was that?
2.2 pounds mass per second squared, sir.
I'd just say per pound of force, that would work for me. And we've got another little problem, and that is this foot inches disagreement problem. So let's just throw another conversion factor in here.
That's what it's all.
Go. Let's see, 12 inches per foot. Second squared go away. And what units will we have that we're left with? Feet. That's how many feet the thing is compressed. If you prefer something else, just, if you prefer inches, just multiply it by 12. All right, so numerically, the 2's cancel. And numerically, we've got 3.23 squared divided by 12 divided by 32.2, square root of the whole thing. Okay. And the units will be feet. So go ahead and calculate that one for me if you would. That was a little friendlier than the last one, wasn't it?
I got 161 feet.
161. Sounds reasonable to me. Anybody else? I don't like close enough. I like to know.
I got 164, but I mean,
Yeah, I got one.
Okay.
Well, anyway, take it and multiply it by 12. Let's get something in inches. The compression of the spring is how much in inches?
1.97.
So about 2 inches or so. A little bit anticlimactic to come up with a number at the end, isn't it? You see, there's so much interesting algebra to play with along the way.
all that for 2 inches.
That's all that for 2 inches. Bless you. Any questions about this problem? Anything you were confused about along the way?
The problem.
The problem? I think what confuses you probably is, number one, breaking up a problem into multiple parts. Right? There was the energy analysis at the beginning, the impact, which is a little bit complicated because of a couple of different coordinate systems, and we needed those coordinate systems to make our lives easier because we knew that, the problem was we had an external force acting. So we ended up with two sum of momentum equations that we had to put together to get rid of what looked like it was unsolved. In fact, we could not solve for the normal force or the time. But notice that the normal force times time actually is the impulse of the ground, isn't it? So if they had asked for the impulse of the ground, we could have given it to them. It would simply been the normal force in B times time, T. We could solve for those two in the product, just not independently. Okay? So it wouldn't have been too bad. It's just something else they could have asked for. Like I said, I doubt that our numbers are quite right. I probably made a mistake along the way somewhere. They at least seem reasonable, so we'll call it good and end this problem, okay?